Christos Papadimitriou, that I have the honor and the pleasure to introduce today, left his native Greece to pursue a PhD at Princeton University. And our acquaintance goes back almost 40 years, because we met at the University of Illinois when he was interviewing after his graduation from PhD. His professional trajectory has been remarkable, really. I mean, he readily established himself as a star in the growing field of theoretical computer science through his contribution to computational complexity, combinatorial optimization, database theory. And in each of these fields, he also established the pedagogy, or contributed a lot to establishing the teaching character. Also very important in more recent time has been his application of computer science notion to game theory through the establishment of algorithmic game theory. His accomplishments are too numerous to be reviewed here, but they've been widely recognized by his community through his election to national prestigious academies and through the award of the Gödel Prize for the theory that led to the creation of the notion of the price of anarchy. On a personal note, let me mention that his work exudes a character of refinement and class that is a clear testimony of his upbringing under the shadows of the great minds, Socrates, Plato, Aristotle, Euclid, that so much have contributed to the culture of the world. Christos Papadimitriou.
This introduction left me speechless. Never introduced somebody, Franco. Yeah, it should be on. Yeah, it's not? Okay, good. Great to be back here. I'm ashamed I haven't been here for so long. It's long ties with Brown, with this university and this department. And it was actually, I should tell you, I had forgotten the pleasures of taking a shower without guilt. Okay, you know, I come from California, so it's perfect. Yes, all right. Yes, all right. Okay, so today I'm going to speak about. My talk will start and end with brains. So these are the giant intellects, some of the greatest intellects of the 20th century, which started computer science, our field, and. Alan Turing and John von Neumann. And of course, this is lecturing in honor of von Neumann. Alan Turing, of course, started computer science by defining what is computation and what is not. And John von Neumann, the great finisher, created the first amazing machine. Let's take store for a moment. All said, we've come a long way, okay? So actually, maybe somewhere here there is also web caching, okay? Internet caching, okay? Right? So nice to connect. Amazing accomplishments, technical, engineering, and conceptual, required a lot of great work and advances in many fields and in many dimensions. And if you ask yourselves, what are the engines? You know, that's an engineering question that propelled all this. There are two answers that I can think of. One is Moore's law, okay? So, and the other is algorithms, all right? I mean, so, yet we are perhaps most famous for the problem we didn't solve, okay? And that's the P equals MB problem. Can exhaustive search can always be curtailed. Just to refer a little to John von Neumann, I don't know if everybody knows how intricately connected with the P versus NP problem is John von Neumann. It so happened that the disconnect between polynomial and exponential time was first, to my knowledge, mentioned in a 1952 paper of his about the assignment problem. The P versus NP question was first articulated in a letter that Gödel sent to von Neumann while von Neumann was sick in his deathbed. And finally, he would have found the problem irresistible. He would have totally worked on it. And for all I know, the problem would have found him irresistible also, right? So that so computer science, it is both a creator and a curator of an essential technology. It is also the source of one of the most fundamental questions in all of science, the P versus NP question. And what else do we do? Okay, so today I'm going to tell you about another thing that we do well, and that's lens on the sciences. Okay, that computer science is also a way of thinking that can make progress, can dissect interesting, hard problems in the sciences. Because computation is everywhere. You know, 250 years ago, I mean, this is also the 250 years theme of the lectures. 250 years ago, there was a bunch of mathematicians, actually exactly 250,000 years ago, 250, sorry, I'm also working on evolution, right? So 250 years ago, Euler published his book on the motion of rigid bodies, okay? And so this really meant that there was a bunch of mathematicians who looked around them, who looked at the sort of empirical problems of the day, and they said, equation, 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 okay? So, you know, and this completely changed the world and the way, the world of science and the world in general, all right? And what I'm saying is that there is computation also everywhere, okay? There is an algorithmic problem embedded in every problem in science. And the real reason, why am I so sure? I see two strains of reasons. One is that in every scientific object of study, there are underlying computational processes, okay? Latent computation. And if it's not in the object, certainly, because our field is very new and recent, but its spirit has been living on, okay? And there have been computational algorithmic aspects in the models that scientists over the centuries had created for these scientific problems. And as a result, we have a lot of work to do, okay? Okay, the main theme, if you wish, of this talk is that the computational point of view, the computational algorithmic worldview, provides new insight into and tests the most prestigious theories in every field. Frankly, in some sense, our discipline was destined to be like that, because you cannot find in the history of science two minds who were so much into risky forays into the far reaches of intellectual life than Alan Turing and John von Neumann. Okay. For example, one important, one example in which I'm not going to dwell much, is statistical physics and algorithms. If you wish, one of the most, here is one catchy way to put it. One of the deepest problems in science is, how does the lake freeze, okay? In other words, why is it that systems of coupled particles, when a certain global parameter changes, completely have a complete transition in their global behavior, okay? And incidentally, von Neumann was very much interested in this. Okay, I don't know if you know, but the quantum generalization of the Gibbs entropy is called the von Neumann entropy. Okay, so and he did work on this in the 30s and 40s. It so turns out that the last 25 years, computer scientists noticed that there is a very tight connection between phase transitions and algorithms, in the following sense, that phase transitions correspond almost precisely, and depending on, it's very context dependent, but many times correspond almost precisely to changes in dramatic changes in the rate of convergence of certain randomized algorithms. Okay, and this has led to a true evolution, the revolution in the field of phase transitions, and it's a scientific revolution, sort of, of a new kind, the interdisciplinary revolution, because you have physicists coming up with very clever algorithms, okay, that are now the champions in some domains, and you have computer scientists write deep papers about physics, okay, so that this happens. All right. The second one is quantum computation, okay, and the protagonist here, the person who opened our eyes to that, is Feynman. Incidentally, von Neumann, 90 years ago, decided to work on quantum mechanics, and the next 6 years he wrote his book on the foundations of quantum physics, I believe it's called, and this book was the dominant way, sort of, the most. It was axiomatic. It was extremely rigorous. It introduced Hilbert spaces. I believe it also introduced the term Hilbert space, okay, in the study of quantum mechanics. And it was the dominant way of learning about quantum mechanics, more specifically the Copenhagen school of quantum mechanics, until Richard Feynman's QED, okay, quantum electrodynamics book. So in the early 1980s, Feynman asked the following question: how does one simulate a system of particles? Okay, and if the system is turns out is classical, he proved by highly non-trivial arguments. So, in other words, the arguments were not mathematically sophisticated, but it was very difficult, very difficult to make the correct choices in every turn of the modeling game. Then they can be simulated essentially in polynomial time efficiently. But if the system is quantum, then he noticed that naively an exponential amount of time is required. Okay, and of course, right after, Feynman did a very Feynman thing. Okay, he turned the question on its head, and he asked, okay, that's a problem, but what if we turn it into an opportunity? What happens if we build a computer out of these things? Okay, and a quantum computer. And of course, exactly 10 years later, this was done. We have at least on paper. And to quote my colleague, who is one of the great contributors into this saga, Umesh Vasirani, he believes that quantum computation. Okay, this was a minority opinion 10 years ago, but now it's a majority opinion. That quantum computation is not about building. Forget computers. Okay, forget quantum computers. Quantum computation is basically it's stretching exercises for quantum physics. Okay, what is stretching test, stretch test for quantum physics. Okay, let's talk about equilibria. Okay. Equilibria are behavior predictions in economics. This is an equilibrium, by the way. it's an equilibrium in the following sense, that a mango would love to be at the bottom of the bowl, okay? But if nobody is moving, it's going to stay there, okay? So that's what an equilibrium is, okay? It's basically a situation where everybody is not incentivized to do anything else than what's happening right now, okay? Given that nobody else will, okay? And it has a fascinating history. First of all, it was discovered by John von Neumann that every game has an equilibrium as long as it is zero-sum and two-person, okay? In other words, almost never, okay? And the great surprise came 22 years later when another Johnny, not pictured, proved that all games have one, okay? And this led to the famous reaction by John von Neumann, who belittled John Nash's, von Neumann was a famous professor. John Nash was defending his PhD thesis. Okay, so that's how he reacted. Okay, yeah. So John von Neumann, whom we all admire immensely, okay, was also the world's sorest second. Okay, yeah. So and let's not forget that John von Neumann had a few years before that written a 700-page book, which in the middle of it had a huge hole with the precise shape of Nash's theorem. Okay, and we can imagine we can all imagine how he felt. Okay, when he saw this. All right, Nash's theorem was sort of revolutionized economics in the sense that, first of all, it was proved Arrow and Debreu, inspired by Nash's theorem. How do I know? Because Ken Arrow told me. Okay, that they looked and said, "Wow, you can prove equilibria theorems by fixed point." Yeah, of course. Yeah. So and soon they had this. Okay, Roger Myerson wrote in '99 that he argued that equilibria are that Nash's theorem essentially, okay, not precisely the Nash equilibrium, but the rigorous notion of rationality that underlies Nash's theorem, and its universality, in other words, the fact that every game has it, okay, have been at the foundations, have been feeding with ideas and foundations all of modern economics. Okay, it turns out that so once you look at this as a computer scientist, okay, you find out that there is something wrong in the sense that Nash proved the theorem in '50. Nobody has published an algorithm for satisfactory for our standards algorithm for finding a Nash equilibrium. Okay, and indeed, like 10 years ago, we proved that it is an intractable problem. All right, and intractability is an issue. Okay, it's not. We are all computer scientists. We are very cynical about NP-completeness. So what? Okay, I solve NP-complete problems 7 before breakfast. Okay, but here's the point, right? That universality is important here, right? If Nash's theorem read that almost all games have a Nash equilibrium, okay, he wouldn't be cited so often, and maybe the Swedish Academy would not be as kind. Okay, so he proved that all games have a Nash equilibrium. Okay, and this says that there are games, however rare and sophisticated counterexamples, where Nash equilibria exist, but they are for all practical purposes beyond reach. Okay, so it will take lifetimes of the universe to actually construct them. Okay, so. And this means really that it cannot be a useful prediction of behavior of a group of people, right? And in the immortal words of Kamal Jain, if your laptop can't find it, neither can the market. Okay, so every time I know there are famous economists in the audience. Okay, every time I talk to economists about, I quote Kamal Jain to economists, we get to a long discussion, at the end of which we agree that okay, the market is not a laptop, but it's a bunch of laptops. Okay, we know in computer science, you know that there is no difference. Okay, so okay, good. Let's talk about evolution. Okay, so when did game theory start? I don't know. Okay, but everybody knows when evolution started. Okay, so it's unlike most scientific endeavors, evolution has an extremely sharp beginning. Okay, it was May of 1959, where Darwin, who here because of Mac Windows incompatibility is hiding his own title. Okay, published his famous Origin of Species. The title has been truncated. Okay, it's a much longer title. Okay, I don't remember. Incidentally, I don't know if you have read this book, but you should. Okay, there is because it's a lesson not in biology, not in evolution. No, it's a lesson in scientific argument. Okay, so in other words, if you want to convince the world about something, okay, read this book first. Okay, so this is Berkeley used to I teach it once in a while when I teach evolution. So we read a chapter every week. But Berkeley used to teach it in the Department of Rhetoric. Okay, because it is a very classical example of scientific rhetoric. Okay, so in any event, I don't know how many of you know. Darwin did not discover evolution. Okay, evolution was almost commonplace. Everybody in 1859 was agreeing that sure, of course, species evolved. Okay. By the way, we are computer scientists. I should tell you this. You know who was one of the evolutionary thinkers before Darwin? Charles Babbage. Okay, our field's granddaddy. Okay, so he wrote about evolution. Okay, in any event. So he did not discover evolution, but he discovered two amazing things. Natural selection, which is the engine of evolution, and actually the hypothesis, the conjecture of common origin, that we all come from a few species. Actually, he said a few, he meant one. Okay. By the way, you can find, there are 9 editions of this book, and you can find in the web a phylogenetic tree of the 9 editions. Okay, so. The funny thing is that you can find what is missing, what happened, how did it change and all that, and one of the most interesting things is the number of mentions of the word God. Okay, and it goes like that. It has a harmonic of 2. Okay, and harmonics of 2, as we know, is about internal conflict, right? So it's really it's really very nice. Okay, so what happened after? It was by far not the last word. Okay, there were like football field size gaps in Darwin's knowledge and reasoning. Okay, and then genetics came. Okay, Mendel did the work and published it in 1866, but everybody ignored it until 35 years later. By the way, we are all scientists who are all very eager to have our work recognized. This is one of the 10 greatest scientific papers of all time. How many citations has he had in his first 35 years? Okay, the answer is 3 by people who had not read it. Okay, and when Mendel went prime time, this created a true crisis in evolution, right? because Mendelianism was perceived to be at loggerheads with Darwinism, okay? And the reason is that Mendel showed us that genes are discrete, right? But whereas Darwin was explicitly mentioning continuous traits, okay? And that was irreconcilable until 30 years later, when if you're a mathematician, seeking more reasons to be proud about math. This is one, okay? That three great mathematicians, Fisher, Wright, and Haldane. Fisher, the same one who founded physics around the same time. Statistics around the same time. So for 20 years, they wrote an amazing opus where they defined the equations of evolution. Okay, these equations are called population genetics. Okay, and I'm not going to show them, but they are the mathematical engine of studying evolution, and one of the great insights that they have, Fisher, Wright, and Haldane, is that they created one particular trait, one particular characteristic, which they called fitness, which was in some sense a summary of all other characteristics, and which corresponds to Darwin's fitness, but its mathematical meaning is very interesting and tangible. Fitness means the number of offspring, the expected number of offspring a particular genotype is likely to have. Okay, and once you have that, the equations essentially write themselves. Okay, you know, and that's what they did. And of course, the last 40 years have been inundated with data. Okay, so you know, so this is a field. Evolution is a field that has been theoretical for 50 years, and suddenly has a lot of data. Okay, so it's a field in trouble, right? Okay. Amazing field. The important questions are unanswered. Okay, so I'll just go through most of the important questions. There's something strange with my. How do complex adaptations happen? Okay, it turns out that in all of these, sort of, you know, computer scientists and my group, mostly, so we have done work on this. Okay, we have new insights that are based on computer science. For example, for the first question, we had a paper in the last Fox, which sort of implicated satisfiability to the study of this question. Why so much genetic diversity? Okay, we are sequencing organisms, and we find that I mean, diversity. All right, I mean, selection is supposed to mean that nature sort of finds the best and keeps the best. Okay, you know, so how we look around you? I mean, how come we are so different? Right? I mean, that does make sense. Okay, and indeed, we measure diversity, and it's at least one order of magnitude more than the theory predicts. Okay, so there is something to be explained there. What is the role of sex in recombination? Okay, so you know, believe it or not, this is an incredible mystery. Okay, so you know, we don't understand. You know, sex seems disadvantageous. Okay, and yet everybody does. I mean, you know, if you look, by the way, ever since I spoke about sex, there is an awkward smile in your face. Okay, that's fine. Don't worry. It happens to everybody. Okay, it means you are not biologists. Okay, you know, so you know what biologists sort of, you know, are completely cool when you mention sex to them. Okay, you know, because when they hear sex, they think of the mystery of recombination in evolution. Okay, right? So it took me a very long time to become biologist in this sense. Right? I mean, so I mean, you know, it is superficially harmful to both organisms and species. Okay, so why is it so widespread? Right? I mean, this is. I mean, there are many, and I'm sure you have heard a lot of explanations. Okay, I'll tell you. The word from the headquarters of evolution theory is that there is no explanation that is enough. Okay, there is no explanation that generalizes and explains why sex. I mean, another thing, I don't know if you know, but that bacteria have sex. Okay, bacteria exchange genes. All right, I mean, they procreate by exchanging genes, and in fact, sort of, you know, they even some of them advertise. Look what I have. I mean, you know, what do you have? Okay, you know, so okay. And here is the final thing is what I'm going to talk more about. Is evolution optimizing something? I mean, if you think about it, sort of, you know, first of all, Why is it interesting to computer scientists? Because there are all these algorithms that assume that evolution is optimizing something. Okay, so and they are mimicking evolution, trying to find the optima. All right, trying to find good solutions. But in fact, all evolutionary thinkers, theorists, starting from Fisher, who thought that there should be an optimization principle, that evolution should be like thermodynamics. Okay, there should be some kind of energy that leads it. Okay. Wright wrote a simple equation for a single gene deployed, and this was an optimality principle, and he challenged his colleagues to generalize it. Sam Carlin, many of you know Anna Carlin, her father, who was an extremely gifted applied mathematician, so who has worked on all the interesting problems in his era. So Sam Carlin wanted, was in a long chase of the evolution's Lyapunov function, okay? And reportedly, this is private communication by 2 or 3 sources. He proved that it exists, but his argument was non-constructive, okay? And it was never published. So what is evolution optimizing? So here is, if you are like me, okay, you are thinking, okay, this is taking too long, okay? What is the one sound bite that I want to remember? Okay, so here it is, all right? Here it comes, all right? So this is something that I hope you remember. That there is a way to look at evolution. So with Eric Chastain, who is a graduate student at Rutgers, Adi Livnat, who is a biologist now at Haifa University, and Umesh Vazirani, my colleague at Berkeley. What we did is we looked at the equations of Fisher and Wright, okay? And we looked at them in a regime that is not very sophisticated, in a regime that everybody assumes is a good assumption. In other words, it's called the weak selection regime, okay? Which means that, well, there is selection, but it's not like extremely strong, okay? So that in most cases it is very weak. It is a weak selection forces. And in this, by looking at the equations, doing some algebraic manipulation, and remembering what we knew about computer science and game theory, there is a connection to to repeated games. So here is a theorem that the equations of evolution, as are believed in the mainstream of biologists. Okay, it's not like we invented a new model of evolution and this happens. Of a population under sex. So sex is important. In other words, sex is what enables this. And frankly, to my mind, even though Adi Livnat cringes every time I tell him that, this is the role of sex in evolution. Okay, so to bring in this point of view. Evolution of population under sex and weak selection is mathematically identical to a repeated game between genes. So evolution of a particular species, okay, you can visualize it, turns out, as the genes of the species sitting around and playing a game, a repeated game, okay? The repetitions are the generations, okay? And the strategies of each gene, so the genes are the players, and the strategies of each gene are its alleles, okay? The variants of the gene, all right? Games are played probabilistically, so they're randomized between these alleles. And the probabilities with which the gene plays these alleles are the frequency of these alleles in the current population mix. Okay?
What is the role of an allele?
An allele is a variant of a gene, okay? It's a variant of a gene. So basically, we have 3 alleles of hemoglobin, okay? So, and one of them, if both mom and dad has it, will get you Mediterranean anemia. Okay, this is so a lot of strengths and weaknesses of a human genotype come from alleles. Okay, so an allele is what is basically the characters. Okay, the digits. Okay, they are not nucleotides. Okay, no. So it's not 3 billion long, it's 20,000 long, okay? So it's every gene, okay? Imagine a 20,000 string that is the genes, okay? And every gene has one of a few characters, right? A, B, C, D, okay? And these are the alleles of this gene, all right? So, and the genes play these are the strategies, right? I mean, the genes play these are the strategies played by the gene. And the randomization is precisely what the population shows. The common utility is the species fitness. So this is not Dawkins' selfish gene, right? I mean, no, this is the community-minded gene, okay? They all want that the boss does well, okay? And the players randomized through multiplicative updates, okay? So now this is really, this really amazed us. This really caught our attention, okay? Because what is multiplicative way updates? Multiplicative updates is a simple common sense algorithm which basically the economists discovered it in the 50s, and they call it Hannan consistency. Then financial mathematicians discovered it in the 80s. Then people in AI discovered it. They called it Winnow. They called it boosting. Okay, they called it and then the theoretical computer science. Theoretical computer science takes credit for discovering it last and not having forgotten it yet. Okay, so it is a very simple and common sense algorithm which is known for its unreasonable aptness. Okay, so in solving problems, it solves problems that it had no right to expect to solve. Okay, basically the whole idea is this: at each step, increase the weight of allele, in other words, the frequency in the population, by a factor of 1 plus f sub I, where f sub I is the allele's fitness in the environment created by the other genes, okay, by the genetic mix of the other genes, okay? And that's the whole algorithm. It turns out that that's what evolution does in this particular regime. And it gets better. Because now you can do, if you do convex optimization duality, you find the following fact, okay, which was a major surprise to us, that every gene acts exactly, so there is no sin worse in evolution than to ascribe teleology to things like organisms, species, genes, and so on, okay? Or evolution even, okay? But what I'm saying is that mathematically, it is the same as these people sitting around playing this game. What they were trying to maximize is the sum of these quantities, okay? These two quantities are, the first one is the entropy. In other words, the genes are keenly interested in diversity, okay? Every gene wants to keep its diversity. And the second part is, first of all, it is multiplied by the selection strength, which I told you is very small, okay? Imagine that this is 1%. So
looking at, you're saying that the entropy is there as a smoothing to make this thing actually optimize something?
you can say it's a regularizer.
Yeah.
It's exactly a regularizer. I don't know why it's there, okay? It's there probably because this is the best that you could do with sex, okay? So
How's the entropy defined?
The entropy is the expectation of the logarithm of 1 over probability. It is basically a classical measure of the standard measure of diversity defined by Shannon. Then the entropy of a distribution. Okay, so the best entropy is to have everybody the same. The highest entropy to have everybody sort of 1/3, 1/3, 1/3. Okay, the worst entropy is to have everybody sort of 1 and everybody 0. Okay, so that's uncertainty, surpriseness. Okay, how much surprised are you sort of when you sample this? Okay, that's.
So is it? Am I to interpret this equation so that each gene seems to X is a vector, yes?
Is a vector, yes, right.
So in what sense is each gene seeking to optimize this? You mean?
So sorry. This vector is specific to this gene.
Yeah.
Okay. This equation, this potential, is specific to that particular gene. Okay. And every other gene will have different. Yeah. Okay.
With its own matrix.
Its own right. Okay. And fitness is only sort of the capital F in the last term, and it is cumulative fitness. First of all, it's multiplied by s, by a small number, okay? So in the beginning, it's not very important. You know, it turns out that the diversity is very important. As it progresses, it becomes more and more important, okay? Sort of, you know, and in the end, of course, it's going to choose one allele and fix there, so you know, and diversity will go. Yeah, but that's asymptotically, okay? So you know, and as we know, life is in the transient, okay? So okay, so this is okay. This is.
But you haven't said how. So S is equivalent to the step size in a traditional sense.
No,
Okay.
no. You
It's
should
a
think
weighing of the-
you should think
It's
it's
not
a
the step size, it's a weighing of how much regularization there is.
it's a weighing of how much regular. If you wish, it is how strong selection forces are.
Yeah, but how does that adapt? How does that change over time?
It doesn't change. I mean, no. You can, you know, it doesn't. You know, it doesn't. You know, you know, it's easier to think that S and the fitness metrics and everything stays the same, okay? But you know, you can imagine that the environment changes, fitness changes, you know, selectivity changes, and so on, okay? You know, Vince.
Please explain what you mean by cumulative here.
Okay, cumulative is, you know, I'm glad you picked it up. Cumulative is a big puzzle. Cumulative means that the first generation has the same effect on what I do next as the last generation. The distant past is equally important as the current.
So it's fully retrospective.
It's fully, yes, yeah. So if you wish, this sum measures total evolutionary success. Okay, now it makes sense, all right? Because it means that, well, if I'm very successful, I don't have to keep diversity so much, okay? Seems that I'm doing something right. Okay, so, okay, let me impress on you, okay? This is not an equation, sort of, you know, that we invented, okay? You know, this is, if the models of Fisher and Wright and so on, so, you know, are right, okay? What I'm saying is that this is apparently what evolution under sex does, okay? It is genes optimizing this thing, okay? So, so what I'm saying is that a lot of the questions of the basic questions, I mean, of the three last basic questions, the role of sex, what is optimizing, why so much diversity, the three last questions, you know, can be informed by this sort of very simple finding. All right, so let me change completely subjects. Vince.
One question which you might defer. The fact that it depends on cumulative history makes it seem very unlikely that the limit points are not history dependent, and yet your punchline is not history dependent.
Right, exactly, yes. So
Put it off until the
right, yes, okay, good, all right, okay, so, oh my God, you have to remind me the sweat books, okay, now suddenly I have anxiety, okay, right, so, okay, so, all right, finally, okay, brain. So, it is the most amazing frontier, okay, so, you know, the most incredible problem in science, okay, you know. It is also, of all the problems in science, it is also the most blatantly computational, okay, I mean, so we should be working on, okay, and on it. It's a shame of us that we have not been working on it, okay, you know, so since the beginning. So actually, von Neumann has worked on it, okay, as von Neumann actually was interested in evolution, but in a way that maybe you...
Turing, at least thought of it.
yeah, definitely. I mean, Turing's original motivation. I mean, if you read his 1937 paper, it's unclear if he's more interested in computation or the brain. Okay, so you know, it's very balanced. Okay. So let me point out something. Okay, that there are some amazing disconnects in the study of the brain. Okay. Babies do amazing things. Okay, computers do amazing things. There is no intersection. So we are very clever. We do make very clever algorithms. You know, once we can't find an algorithm, we prove our problem semi-complete. Okay, so the brain always does it and does it in a different way. Okay, so we we are very much like evolution here. Okay, we have an amazing deluge of an extreme deluge of data. We understand better and better and better about anatomy, function, neurons, synapses, and so on. And yet there is no overarching theory at the horizon, below the horizon, anywhere you want, sort of, that of how this gets together, how this comes together. Okay, we come up with great algorithms, and this includes deep learning, and yet you can't look the audience in the, with a straight face and claim that, well, and maybe, maybe that's how the brain does it. Okay. I do not know of an algorithm for solving a non-trivial problem where you can do that. Okay, and that includes deep learning. And of course, there are some insights that we know the last 10, 15 years we have known about the brain that change a little our conception. For example, we know that vision goes from GNC to NGP, LGN. Sorry, the lateral genicular nucleus. Sorry, yes, yeah. So I just can't extract initials. Okay, so to V1, to V2, to V4, and so on. But we have known for a long time that a lot of the connections go backwards. Okay, they go in the wrong direction, right? I mean, and presumably much of the traffic will go in the wrong direction. We know that prediction is very much involved. Okay, to quote Jeff Hawkins on that, a vision scene, it's much closer. In other words, what our eye does, sort of, every millisecond of our existence, the problem it solves, it's much closer to a poem than to a painting. Okay, because whenever I look one face in the audience, okay, my eye does sort of 12 forays called saccades, sort of, and sort of, and composes. So it's a poem. And the reason is to predict. Okay, so so I'm looking to this man's left eye, look to the right, and if there is no nose, please tell me because something very important happened. Okay, so yeah. And there is also reciprocity and clustering. Okay, that the brain is not a random directed graph, but there are a lot of sort of it's very much like the internet. Okay, and for example, okay, reciprocity. The chance that there is a synapse from this neuron to this neuron is 10 to the minus 7. But given that it exists, the chance that there is a connection back, depending on which paper you read, is between 10% and 50%. Okay. So there is something going on. I mean, there is a lot of this. In any event, our next speaker. I told you shame on us for not working on this brain. I should say shame on us except for less, okay? Because Les Valiant, okay, true to his last name, okay, so has been bravely working on neuroscience since the 90s, okay, since the early 90s, and I mean, I'll say more about his work, and he will say much more, I hope. One of his points is that theory is essential. Okay, so even though Ramon y Cajal despised theory, that then he proposed an actually rigorous model of algorithms in the brain. And then he introduced a beautiful concept of items and operational items. So I'm going to tell you. So I'm not going to explain what this means, but basically what I want to tell you is that Les's neuroidal model is sort of an automata theoretic model of any algorithm that you can claim runs in the brain should obey. Okay, now should be writable in this model, and it's a distributed model of computation that is incredibly austere. Okay, just to scare of those of you who do distributed computation. Here is only communication between I and J that can happen. Okay, I can communicate something to J. If I fires, and it's so lucky that enough other people fire, that J ends up sort of, that the sum of the synaptic weights is enough for J to fire. Okay, this is the only communication that can happen. All right, so both hands and both feet tied behind. Okay, so to proceed, so it's a formal model of cortical computation, which is very conservative. In other words, it is explicit design, so nobody can say, I think I'm quoting from Les's paper now, well, I don't think neurons can do that, okay? This is something that neurons can do, okay? But a word of caution, okay? That this is not the kind of distributed computational model that macho hackers can sort of, can take on and say, okay, I guess I can sort in n log n in this model, right? I mean, that, in other words, it's not meant to be abused, okay? It's, you should program it with reverence and humility, okay? And sort of, and keep in mind what you are after. Okay. So what is an item? An item is a set of R neurons, and it represents a real-world object, idea, concept, like almond, let's say. Simultaneous firing of these neurons means that you are thinking this idea. Okay, so we know that when you are thinking of something, a lot of things light up. Okay, that we know. Well, what the variance model concept of item says is maybe this means that this real-world idea corresponds to an item. Okay, so now these are all the R neurons which are associated with this item, and it turns out that for all we know about the brain and the numbers of the brain and the amount of randomness that exists in it, you can find reasonable numbers of R so that everything that I'm going to tell you works. And then very important is variance operations on items. Imagine that you have A, let's say for almond, okay? And then you have another item, B. What do you want to stand for? Let's say butter? Okay, butter, all right. And then you want, every time you think both of almond and butter, to think of almond butter. You learn that almond butter exists, okay? So this is the join of A and B, okay? You create a join of these items. And every time both of them simultaneously fire, then almond butter will fire, okay? And finally, there is a second operation, and there are several more that I'm not going to talk about. Imagine that you have almond, and then you learn the concept of you have the concept of healthy food, and suddenly you read that almonds are healthy, all right? I mean, so you want to link almonds to health. So every time almond fires, then healthy food will fire in the future. Okay. Okay. So these are the two operations, and the theorem is that in two steps, join and link had to be implemented by vicinal algorithms, by these algorithms, okay, by these minimalistic distributed algorithms that model what can be done in the brain. And in fact, using join and link, you can obviously learn patterns of length too. Okay, you can, in the sense, you can define any relationship you want between real-world objects. And he left open what happens. What do you need in order to go beyond two? To more than binary relations. And with Santos Vempala, we have in the next call, we have a paper where we go a little beyond and we do the following. We come up with a new primitive, which we call, it's an extension of join, which we call predictive join, okay? And our mindset was we wanted to basically have something which will include downward traffic and prediction, all right? I mean, this was basically our mindset. And here is what predictive join is. It's join, if both A and B fire simultaneously, then P join AB will also fire, but there is more. You imagine that only A fires. Then P join does not fire, but it gets mobilized, okay? And then it predicts B, all right? And basically it goes down and says, hey, B, are you here? And now B could be P join itself, right? In which case it will go down and say to your C and D, are you guys here? Okay? Because somebody is asking for me, all right? So this is the whole idea. And we proved that you can implement it by this null algorithm in 3 steps. And it turns out that you can learn patterns with this, okay? And I'll just play you the movie. Basically, what we assume is that, as you are going to see, the algorithm is very minimalistic, as I implored you to do, okay, when you program in this model. It basically says, you know, you are stimulated by outside stimuli, and when you are, do your thing, okay? That's and do your thing forever, okay? This is the only algorithm that will be acceptable. And here is what happens: that the pattern, you know, the digits in the pattern fire at random, sort of, you know, at each point. And when they fire, maybe they get the appetite to form a P join, and this happens again at random. And then maybe other things for P join, other things for P join, and so on, and so forth. Now the point is that if this pattern is presented again, then here's what happens. The fires happen. The items fire, the inputs, then this will fire. You see, it will not fire, will be mobilized, okay? And is going to ask for the partner 0. It says, hey, it's here. In which case it will fire, and this will fire also, right? And now, since this guy fired 0, this is going to be mobilized and look for the 0, and it's still here, okay, and so on. And now it will fire, and this will fire, and so on. Okay, so this is how in the second presentation exactly the right thing will happen. Of course, other things will happen, but with high probability, exactly the right thing will happen. Finally, if a different pattern appears, then what will happen? In other words, if the bits, the first and third bits are changed to 0 and 1, then let's see what happens. This fires. These two are mobilized. They look downward. Only the 0 is right. This guy fires. But now, because this fired, also this fires, this is created, and so on. So basically, you reuse the part of the data structure that the other pattern has created already, and you add what you have in order to learn the pattern. What does it mean to learn the pattern? I propose the following definition. On presentation of this pattern, you create a top-level item, let's call it representative of I of x, which, in the invariant of x, which will not participate in further P joins, and will fire precisely on all subsequent presentations of x and not otherwise. And the algorithm is the following. Repeat for S steps. Each sensor input is sensed with probability P. P joins are created with probability Q after retraction delay D. In other words, you have to introduce a delay to keep things at bay. And the theorem says that any M patterns in 0, 1 to 10 can be learned with high probability, and with a DAG, with a structure, data structure, that has total height log M plus log N. In other words, the number of patterns, the logarithm of patterns plus the logarithm of the pattern length, provided that the delay is long enough and you leave the pattern long enough for it to be recognized. Okay, we have simulations. We run it on patterns with 100 bits. All learning activities completed with 80 steps. You see, this is another strict model, another strictness of the model. It's not big O, right? Forget this, right? No, if it's more than 50, you are out of the picture, right? I mean, because we know that how things happen after 150 milliseconds, okay? So 80 is too much. The sharing is as predicted, and actually the majority of traffic goes downwards, okay, as we wanted. So I'll leave you with this. Oops, I'm out of time. But I'll leave you with the following. What if the mind emerges? In other words, here is how we started working on this. Santos came to Berkeley, and we took a walk in the hills, and we were discussing the following question. If you were building a brain from scratch, which algorithms would you include? Then we said maybe some kind of convex programming. Perhaps you are going to have some majority, you have gates, and so on and all that. I mean, so we were shooting algorithmic ideas back and forth. Depth first search, nah. Okay, so and all that, and then we looked at each other and said, what if there is no algorithms in the brain? Okay, what if everything happens upstairs is basically a bunch of very rudimentary primitives that except that you have 10 billions of them, okay? And in other words, what if it's basically the area size of the cortex that is and of course, another thing that's important, okay? If you take the same cortex and you put it on a boring planet, nothing will happen, okay? I assure you, all right? I mean, so, it's the fact that we have an interesting planet, okay? Sort of, and our cortex and our planet sort of, are best matches, okay? So that's, what if this is what happened, okay? And just to go one step further, language is an organic environment which you created 50,000 years ago. It is revolutionary. Evolutionarily, it's a last-minute adaptation. So, we haven't changed since then. And the hypothesis is that it evolved so as to exploit our brain strengths, okay? And therefore, studying language should give us clues of what are our brain strengths. And by the way, P-join and P-link, which I didn't define, are ideally suited for learning grammar. All right. So I know. I didn't talk at all about the 250 years question. Right? So this is the wrong discipline to ask this question. Right? I mean, I'll tell you. 15 years ago, IT companies were sort of contemplating whether the TV or the laptop will be sort of, and so would be the killer platform of the future, right? So and top execs were talking on their cell phones about this dilemma, and they didn't see the cell phone, okay? So that there will be 10 billion cell phones, right? I'll tell you a personal embarrassing story of the same kind. I cleaned my office 3 years ago, and I threw away a book which I bought. It was published in '94. I probably bought it in '95, and the title was The Whole Internet, okay? So in 1995, I believed that it was worth buying a book that will tell you what is in the internet, okay? Yeah, so, okay, so, I guess O'Reilly should be more, who published it, should be more embarrassed, right? So what, I am going to venture out and tell you my prediction for the next 250 years, that understanding scientific problems in terms of algorithmic ideas will be as widespread and as productive as formulating scientific problems in terms of equations has been during the past 250 years. Thank you.